This video is for Lab 10, Measuring Field Effect Transistors. In particular, it's the second part of the lab, after we've already soldered the transistors onto a breakup board, testing them and seeing how they behave. Let's take a look first at simple tests. We've got the soldered board here with the P transistor on the left and the N transistor on the right. The outer pair of pins are the gates. The next pair of pins in are the sources, and this pin in the very center there is the drain. We can use a multimeter to do some simple testing to see whether or not there are any problems with the soldering. The setting I've got here, let's put that onto the screen if I can, is the diode connectivity test here. And what that does is it puts a 1 milliamp current starting with positive on the red lead and negative on the black lead, and measures the voltage. If the voltage is low, it beeps and it shows you what the voltage across it is. If the voltage is high, it just shows you this overflow symbol. And what we want to do is to check, we can check first of all to see if the gate is shorted to anything by putting one end pin on the gate and just checking each of the other pins to see if there's any shorts. No shorts, we're doing good. You can do that for the other gate also. Then we want to check the source to drain, because that would be in one direction the body diode and in the other direction the off transistor. So how do we check the body diode for the FET? Well, if the source is positive and the drain is negative, we shouldn't see anything. That's the off transistor. But if we swap the two, we should see a diode drop. So that was the source being negative and the drain being positive. Nothing. Turning it the other way around, the source being positive and the drain being negative, and we're seeing about 0.39 volts. So that sounds like the body diode for for the power transistor. The body diode having about 0.4 volts at a milliamp seems okay. We can do the same tests on the PFET and should get similar results. If you put it forward biased for the body diode, you get about 0.4 volts. If you do it reverse body bias for the body diode, you shouldn't get any current through it. Okay, so that's all you need to do with the multimeter is check that transistor. The next thing that we're going to want to do is to run this thing without any load, but check to make sure that it switches correctly. So let's take a look at the schematic here. The schematic part on the left here is what's on that board. The bypass capacitor, the pin for the power supply, the pin for ground, the two gate pins, the drain pin. Here I show it connected up to a loudspeaker, which we'll look at in a little bit, but first let's do some tests with the loudspeaker just disconnected. No loudspeaker in the system. What you're going to want to do is to take a look at how fast you're driving that output pin given different input configurations. So just without any load, how fast does the thing switch? And that's going to be like 4 different things for you to test. Driving them directly from function generator, driving them by a comparator, driving them from 74 AC04 inverter, and then driving each one with a separate inverter, each of the two gates with a separate inverter. So there's several different tests you're going to want to do on that. I'm just going to look at one of those tests, and that's the one where I drive them directly from the function generator. So let's go back to the desk here and see what we've got. I've hooked up the yellow wire, which is the function generator, to the two gates. Well, I'll have it to the two gates if I move the board over where those are. So, 2 yellow wires are now the two gates. The first channel, channel 1 here, is hooked up to just the function generator, to the gates. Because I want to look at the gate voltage. No matter how I'm driving it, I'm going to want to look at the gate voltage. And then the blue channel, channel 2, is hooked up to the drain. And I'm using ground reference for both of these. I have got a power supply here, and the power supply is driving the PFET, and the ground is on the source for the FET. So this is the standard CMOS configuration. Now let's take a look at how it works. Okay, I don't need the schematic anymore. Let's look at waveforms. Okay, right now I've got this thing with the scope is running. I'm running at 2 milliseconds per division. I'm going to want to have the wave gen. I'm going to run this as a pulse between 0 and a positive voltage. And I'll do a 3-volt pulse here. You can do 5-volt pulse. 3-volt works okay. If you do too small voltage, then you won't get up to the threshold voltages of the field effect transistors and you won't turn things on. So you might even want to play a little bit with that and see, hey, when does this thing start working? But I'm doing this thing with 100 hertz pulse of 3 volts. All right, let's turn that on. Power supply, I'm running the same 3 volts there. All right, now let's look at what the scope is doing. All right, the channel 1 here is going from 0 volts to 3 volts. I'm triggering on the rising edge at 1.5 volts, so I'm getting sort of right in the middle there. And we can see that the blue channel, the drain channel, is switching at the same time, going in the opposite direction. That's great. We expected this thing to behave like an inverter, so everything seems to be functioning normally, but what we really want to look at is how fast is it? And at this thing it just looks, oh, it's instantaneous, 1 pixel wide, sort of useless. But we could change, because we're triggering right on the rising edge here of 1.5 volts, we can change this time base to something much smaller, like 200 nanoseconds per division. And now we can see in quite a bit of detail what's going on there. We've got the input rising, we've got kind of the Miller plateau happening here, and we've got some ringing going on here because it's a capacitive load and there's some inductance there. So the inductor and the capacitor have a resonant frequency, which I suspect is about what this ringing is that we're seeing. Okay, so what we're interested in is the fall time here for this edge. Well, if we turn on measurements, we can select, I've already done this ahead of time, we can select the rise time and the fall time for channel 2 and look and see that we're getting roughly 72 or 73 nanoseconds as that fall time. If we wanted to look at the rise time, it's not visible in this window, but if we change the triggering condition from rising to falling, we can now look at the, notice that's on channel 1, so falling on channel 1 is rising on channel 2. We can now look at this channel 2 edge and see that it's going at about 52 or 53 nanoseconds. So we've got a fairly fast transition here, and that's great. You're going to want to measure those transitions with different driving signals for your gate and take a look at what they are. And of course, as always, you're going to want to export the values so you have plots for your pictures that are not plots for your report that are not just low quality screenshots. Okay, what else do we want to do now? Well, let's go back to looking at that half H bridge. The other thing we're going to want to do is to take a look at what happens when we put a load on here. And there's several different things we want to look at with this load. Here I've got the load to 5 volts, so I'm basically only the NFET is really doing much here. It turning on or off to produce current through here or no current through here. But if I switch the PFET at the same time, that means that when the NFET is off, I've got a really good connection back to the PFET. And if you remember, the loudspeaker is basically an inductive load, so if we didn't have that connection back to the power supply here, we would end up with voltage spikes. In fact, one of the things you're going to want to do here is to play around with different connections for what do I do with the PFET source, what do I do with the PFET gate here, to see what sort of voltage spikes you get with different configurations here. The simplest configuration is just to keep this thing as a CMOS inverter, so the two gates are tied together and the PFET is tied up to the power supply. So let's go back to the desktop here and do that configuration. You'll have to experiment with the other configurations on your own. But I've got a loudspeaker here that I'm plugging in now. I hope. And you can see I've got the 3 volts. They are making a loud sound. It didn't really change here, the rise time or the fall time by much. Basically, with this configuration, the inductive load is not making a huge difference. There doesn't seem to be any more overshoot here. I mean, that's the inductive spike there. It's no bigger than it was before, really. We're not seeing much of a problem. You might see more if we looked at somewhat higher frequency. So let's take this frequency up from 100 hertz up to, say, let's try 20 kilohertz. Okay, so let's see what the scope is showing now. Pretty much the same thing. So this output stage is working just great with a load, whether we're doing it at 20 kilohertz or at 100 hertz, doesn't seem to be making much difference. When you try doing this with other configurations where you don't have that good path back to the power supply to suppress the voltage spike, you'll see some rather more interesting behavior. And I'm deliberately not showing you that in the video because I want you to see it for yourself. And so that's basically it for this lab, is do some testing without the loudspeaker there, and then do a whole bunch of different tests with the loudspeaker in place as a load. Here I've shown the load going up to 5 volts to test the NFET. You can also take the load so it goes down to ground, so you're testing the PFET and doing various things with the NFET to see what the inductive spikes look like when you do it the other way around. That's basically it. Have fun exploring these transistors.